everyone. I welcome all of you for CAENexus basic training. So this training is mostly focused on abstract model authoring, and we will be dividing this training session into three sessions. So first session we'll talk about what is CAENexus and how exactly the CAENexus workflow is. In second session, we'll see some details related to abstract model authoring. And in third session, we will see some product efficiency improvement tools in CAENexus. So before switching to this session, maybe I'll cover some key points. So this CAENexus training is mainly focused for CA analysts. Secondly, this is not a solver training, rather it is a prerequisite. Remember that CAENexus is a knowledge capture tool and workflow automation tool. So it initially requires some extra efforts as compared to your traditional approach. But we need to accept the fact that the authoring of abstract model file, it's a one-time activity, and that is going to save a lot of time of analyst in the production work. And lastly, this CAE workflow automation is a team effort and is going to add a lot of value to an organization. So with this, let's start with our first session. So the agenda would be, we will first see what is CAENexus, then we'll see some details about CA geometry, some details related to abstract model authoring, like what is abstract class, what are abstract models, and towards the end we'll see the CAENexus workflow. So let's first understand what is CAENexus. So CAENexus is actually a preprocessor which is based on unique abstract modeling technology. So automation of CA workflow is the central idea or the concept behind this product. So if you see any analysis domain, it is subdivided into three domains, that is pre-processing, processing, and your post-processing. So CAENexus basically falls into pre-processing domain. So it's a preprocessor which is based on abstract modeling technology, as well as the CAENexus report framework. It helps to generate automatic simulation report. So CAENexus falls in two domains, pre-processing as well as in the post-processing. Again, in CAENexus, we supported all CAD softwares like your Creo, SpaceClaim, SolidWorks, UGNX, as well as we supported all FEA solvers like Abacus, ANSYS, OptiStruct, Nastran, and Calculus. So I hope everybody has understood what is CAENexus. So CAENexus is a preprocessor which is based on abstract modeling technology, as well as CAENexus report framework. It helps to generate automatic simulation report. Let's now see a real geometry which is easy to understand and visualize from topological point of view. So you can see on the screen, this is one cube structure, and if you see, this cube structure is made up of 6 faces, some edges, that is 12 edges, and vertices, that is 8 vertices. Also, there is a region inside of this cube which is a part of this volume. So topologically, we can say that this volume is made up of a region, faces, edges, and vertices. Similarly, if I see any particular surface, then I can say that topologically it is made up of face, 4 edges, and 4 vertices. Likewise, if I see any particular face, then it will have two sides. So one is pointing inside the volume and one is towards the void, that is away from the volume. So remember that any computational domain we can topologically define with the help of region, faces, edges and vertices. So every CAE geometry can be defined with topological connection of your region, faces, edges and vertices. Now for practical purposes, we need to have a non-manifold model of our computational domain, and that is required in order to carry out the meshing with different volumes in a geometry. So let's first understand what is non-manifold model. So you can see on screen there are two volumes, volume 1 and volume 2. So these two volumes represents two cube structures and they are touching with each other. Now in CAD model, there would be two surfaces at the interface of these two volumes. So one surface belonging to volume 1 and another surface belonging to volume 2. But in non-manifold model, there would be only one surface and that surface is common between these two volumes. So that common face, we can say that is the relation of these two volumes. So similarly, one can define a relation between this face and the outside region, that is void region. So just remember that in a computational domain, relations can be defined between different geometrical entities. Now, like cube structure, all other CAE geometry or all other practical CAE geometry one can define with the help of topological connection consisting of your region, faces, edges and vertices. So understanding the topology of CAE geometry, it is very easy because we can visualize it, and in traditional approach these CAE geometry they are the starting point of your simulation. So up till now we have seen what is CAE geometry, how one can define the topological connection of that CAE geometry. We have seen what is non-manifold model. We have seen how the relation is or how one can set the relation between the geometrical entities, and that's all related to the CAE geometry, which is your starting point of the simulation in traditional approach. So up till now we have talked about the geometry. We'll now replace the geometry with abstract. So firstly, what exactly the abstract means? So the dictionary definition of abstract is something that exists in thought or as an idea but not having any physical or concrete existence. So if we see some examples like color, so color is an abstract term, while when we say blue color, then blue is a concrete term. Now let's think from the simulation point of view. So when I say solid, then the solid is an abstract term and it can represent any geometrical entity having three dimensions. But when I'll say board, then I'm talking about a particular geometrical entity which has a 3D dimension and has some particular shape. So the terms fluid and solid, they represent some kind of three-dimensional object but without any particular shape. Whereas the terms like bolt or the pipe, they have the definite shape and they have the definite dimension. So the abstract class, we can define the various abstract classes like solid, fluid, size, etc., which can be used to define simulation physics independent of your geometry. So in traditional workflow, we are using CAE geometry to set up the physics, whereas in CAENexus workflow we are using abstract classes, and that's why we can set up the simulation independent of the geometry. Let's see some more details about abstract class. When I'm saying solid class, it only helps me to visualize a three-dimensional object, but it does not help me to visualize how exactly it looks like. So abstract classes are actually the entities which are having some definite dimensions like 3D, 2D, 1D or 0D, but does not have any specific shape. So we have seen in the CA geometry that CA geometry can be defined with the topological connections like region, faces, vertices, edges. So similarly, abstract classes, they can be defined with the imaginary closure entities. So for example, if I'm saying a solid class, then you can see this cube structure, it is just shown for the understanding purpose, it is actually a grayed out. So this solid class will have all the imaginary closure entities like your boundary, interface, your interior, which is your synonymous with the topological connections of your CA geometry. So whatever terminologies we have seen for CA geometry, like their topological connection, their relation, so all those things are applicable to abstract classes also. The only difference is abstract classes, they do not define or they do not have any specific shape, whereas CA geometry, it has a particular shape. So in traditional workflow, analysts, they are using CA geometry to set up the simulation physics, whereas in CAENexus workflow we are going to use the abstract classes which are having some specific dimensions like 3D, 2D, 1D or 0D, but not having a definite shape. So we are going to use these classes to set up the physics. So this is the major difference. So one can have any number of classes like solid, maybe size, maybe contact, to capture the different physics related to your analysis. So we'll see what is the advantage of setting up the physics on the abstract classes as compared to your traditional workflow in the coming presentation. So the abstract class is an imaginary object, but it do have geometrical interpretation in terms of dimension, its closures and relation with other classes, which is similar to the real geometry objects. Now, in order to get a concrete representation of abstract class, it needs to be combined with real geometry. And the reality depends on the geometry the class is combined with. So when I'm saying solid, that solid class can be evaluated to a cube structure or it can be evaluated to a pipe structure depending upon what is present in the CAD or the geometry. Let's have a quick summary about abstract class. So we can define various abstract classes like solid, size, fluid, which can be used to define simulation physics independent of the geometry. So as I said, abstract classes, those are the entities which had some specific dimensions like 3D, 2D, 1D or 0D, but does not have any specific shape. So when I'm saying a three-dimensional class, for example solid, then it can be a cube structure or it can be a cylindrical structure or it can be a engine block, depend upon the CAD geometry. Similarly, the two-dimensional class, so if I'm saying shell underscore 2D is my class, then it can be a rectangular surface or a circular surface or the panels of your cap structure. Same applies to the 1D class as well as the 0D class. So 1D class can be any entity having one dimensional and that can be a rectangular edge, a circular edge, or a zigzag edge. And zero dimensional entity would be always a vertex. So just to summarize, abstract class. So abstract class or the abstract classes are the entities which are having some particular dimension like 3D, 2D, 1D or 0D, but does not have any specific shape unless and until we combine that class with the CAD geometry. Let's have a quick comparison between CAE geometry and abstract class. So we know that CAE geometry, it represents some specific dimension like 3D, 2D, 1D or 0D. Similarly, abstract class also represent specific dimension like 3D, 2D, 1D or 0D. Major difference is CAE geometry, it has a specific shape. For example, when I'm considering a cube CAD part, then I can see the shape of the CAE geometry, or I can visualize it very easily. But when I'm seeing a solid class, then that solid class can be a cube structure or a cylindrical structure, or it can be a engine block. So abstract class, it is not having any specific shape. CAE geometry and abstract class both are having enclosure entities. So in CAE geometry, region, faces, vertices, edges are their enclosure entities, whereas in abstract classes, the enclosure entities are the boundary, interface, interior, etc. Now, when I see the enclosure entities of CA geometry, then it includes the region, faces, edges, and vertices. So similarly, the enclosure entities of abstract class, it includes the boundary, interface, interior, and prune. So if I am taking an example of cube geometry, then it is made up of a region, faces, edges, and vertices. Similarly, if I take any abstract class, then that class also has a respective enclosure entities. So that's all about abstract class. So up till now we have seen what is abstract class, how exactly it differs from the CA geometry, what are the enclosure entities. So now going further, we will see how one can use the abstract classes in CAENexus workflow and set up the simulation physics. We have seen abstract classes. So those abstract classes are used in the abstract model to set up the physics. So let's now see some basics of abstract model. So abstract model, those are made up of four building blocks. So the first one is the components. It actually represents the geometrical entity. These components act as a geometric placeholder. So for example, pipe or maybe engine block or maybe bolt, these are the component which represents the geometrical entities. Second building block is the class. So we have seen a lot about the abstract class. So classes are the entities which has some specific dimension but does not have any specific shape. So one can create any number of classes, for example, a solid to represent a simulation physics like element set. One can create classes like contact to represent contact related physics. One can create size class to set up the mesh size related physics. So any number of classes can be created which will represent your simulation physics. Again, we have seen there are closure entities for the classes. So closure entity, for example, boundary will have two face uses. So one is pointing outside the boundary and one is pointing inside the boundary. So these kind of closure entities can also be used to set up the physics in the abstract model. So if we add any other class, then the common entity between two classes is represented by a relation. And that relation we can use for again to set up the physics in the abstract model file. The fourth building block is the attribute, which is actually a behavior. which we use to attach on a simulation classes. For example, element set attribute, we just specify it on the solid simulation class. So please note that the behavior of the attribute, we are specifying it on the classes and not on the components. And that's the reason, or that's the main difference between the traditional workflow and CAENexus workflow. So in traditional one, we are directly setting up the physics on the CAE geometry, whereas in CAENexus workflow, we are setting up the physics through attributes on the simulation classes. Now, here is the schematic of abstract model. So you can see here the pipe represents the component, and the solid and size, these are the classes which are assigned to this component. Now one can assign any number of classes based on the simulation physics. So here only two classes are shown, but one can have any number of classes based on the requirement. The triangle shown here, those represents the attributes. So the attributes, those are specified on the classes, on the relation of the classes, or those can be specified on the enclosure entities of the classes based on the requirement. So you can have as many classes as you want, and you can assign it onto the component. So the physics which we are setting up through the attribute, for example, the element set or the material physics which we are specifying through attribute onto particular class, it will get transferred onto your component. Similarly, the physics like mesh curvature, mesh size, which you are specifying on the size class through attribute, it will get transferred onto the component. So this way one can assign as many classes as want, and that actually makes the abstract model file usable across different CAD models. Also, it ensures that it captures the physics in a tiny and reusable abstract models. So, like real geometry contains various volumes, abstract model also contains various abstract classes and their respective relations. So when those abstract models we combine with real geometry, it will give a concrete representation of CAE simulation model. Thus the behavior of classes and the relation will be determined by the real geometry which is combined with that abstract model. For example, if you see this model 1, and if I find out the relation between these two classes, then it will represent the common geometrical entity or the common geometrical face between these two classes. But when I try to find the relation between these two classes here in this model 2, then it will not represent any geometrical entity because there is no common entities between these two classes. In a nutshell, if I want to tell you the difference between traditional approach and CAENexus approach, then in traditional approach, let's say I'm dealing with this CAD model, and if I want to transfer or if I want to set up a physics related to elements at solid onto these CAD parts, then I'll do it manually and I'll make sure that all the parts, those are having the solid element set related physics, and that will give me my intended input depth. So tomorrow when I'm dealing with some other CAD model, I repeat the same procedure manually and I make sure that the solid element set related physics, it is getting applied to my intended CAD parts or not. But in CAENexus approach, when I'm dealing with my CAD model 1, I'll set up the physics onto an abstract class in my abstract model file, and I'll just make sure that this class is present in my CAD model, and that will give me the intended element set related physics. So tomorrow when my CAD model changes, then I don't have to repeat the procedure. I only have to make sure that this abstract class is present in my CAD model, and when I'm linking my abstract model file with the CAD model, then automatically the physics related to solid element set, it gets transferred onto the required part. So this is the major difference. In traditional approach, we are using CA geometry to set up the physics, whereas in CAENexus approach, we are using the abstract classes to set up the physics. Up till now, we have seen what is CA geometry, what are abstract classes, what are abstract models. Now we'll have an overview about a CAENexus workflow. So CAENexus, it separates the engineering task in two roles. So one is a role of CAD specialist and another is a role of CA analyst. So CAD specialist, they'll create the computational domain required for the analysis. Also, they'll attach some string parameters to their CAD model. So we call it as a tagging. So adding string parameters means assigning the component and classes to your CAD part based on the requirement. On the other hand, the analyst, they'll author the abstract model file, and for that they will import the classes or the string parameters from the CAD model into a CAENexus. So those imported classes or the string parameters will act as the abstract geometric entities. So those abstract geometric entities will be used by analysts to set up the physics in the abstract model file with the help of attribute. For example, physics related to your element set, related to your material, boundary condition, your loading, your contact, everything will be set up with the help of those classes in the abstract model file. So once done with that, the analyst will create the simulation model by combining your CAD model and abstract model file, and then will proceed for the meshing and the creation of input data. Now, analysts will cross verify that everything or all the physics is getting transferred exactly onto the required CAD part. If needed, they'll update the abstract model file. Otherwise, that abstract model file is published within the organization to be used with the different CAD models. This is authoring mode. Now once your abstract model file is standardized, then you can use the production mode where you have to just use your CAD model and the standardized abstract model file, and the rest everything will happen automatically. That is creation of your simulation model, mesh model, and the input tech creation. So this is the overview about CAENexus workflow. Just to summarize, we have the CAD model from CAD specialist, we have standardized abstract model file from analyst, and when we synchronize both these things, the rest all steps are automatic. That is creation of simulation model, creation of mesh model, and creation of input tech. So these are the three simple and reliable steps, and one can use the Python script to carry out these three steps automatic. So you can use the script for multiple models and you can generate the input decks without any human intervention. Let's now see how the standardized abstract model file is applicable to different CAD models. So let's say we have two different CAD models. So this is the CAD model 1 and this is the CAD model 2. Both are different CAD models, and we have created a standardized abstract model file, and when we synchronize this abstract model file, with the respective CAD models, then we get the respective simulation model, we get the respective mesh model, and we get the respective input deck, which when we submit to solver we'll get the respective results. Now how this one or the standardized abstract model file is applicable to both the CADs which are having different geometry or different topology. So the reason is we are using the abstract classes in the abstract model to set up the physics, and we are making sure that these classes are present in my CAD model. So that's the reason that we can use the standardized abstract model file with multiple CAD models. With this, we are done with our first session. So just a quick recap, we have seen what is CAE geometry, we have seen what are abstract classes, we have seen their enclosure entities, we have talked about or we have seen what exactly the abstract models are. And towards the end, we have just seen an overview about CAENexus workflow. If you have any queries, then please feel free to contact at support@novusnexus.com and we'll get back to you accordingly. Now in next session, we will see some more details about authoring abstract model file. So till then, have a good day. Bye.